All right. So in this question, we have two things that we're going to be asked to do. We're going to be asked to verify things, and we're going to be asked to prove things. Verifying is going to be a little bit annoying, because if you prove things, you don't need to verify them, because what a proof does is it says it works for all angles. But verifying, all you're going to do is check one angle and see if it's true or not. So when we verify for theta equals 30 degrees, so here in part A, again, we could write out the equation that we want to verify, split it up so we have a left side and a right side, and plug in 30 degrees. And do that on both sides. Now, of all those values, which is the easiest one to figure out? Secant of 30 degrees or cos of 30 degrees? Cos of 30 degrees, so let's start with that. 1 plus what is cos of 30 degrees? Square root of 3 over 2. Good. So then what is secant of 30 degrees going to be? It's 2 over root 3. Since secant is the reciprocal of cos, and since cos is root 3 over 2, then secant is 2 over root 3. Now what we need to do is we need to make both of these look the same. So we need to either change the left side or the right side so that they're identical. What can we do here? Does it make sense that you could distribute this to get rid of the brackets? And 2 over root 3 times 1 would be 2 over root 3. And over here, when you multiply the tops and multiply the bottoms, you get 2 over root 3 divided by 2 over root 3, which that simplifies to just be 1. Can you see that they're the same? Therefore, the left side is equal to the right side. And you verified it for one angle. How many more angles would you have to verify for it till you've done them all? Oi. All of them. Lots of them. So that's where the proving part comes in. So what we've done right here is we verified it. That's part A. If we did part B, and had we done part B first, which was proving it means it works for all angles. So you wouldn't have to verify it for 30. You would know it works for 30 and 45 and 60 and even values like 12 and 22 and 39, every single angle possible. So that's the nice thing about a proof. Am I okay to erase this? So the proof, well, that is what we were doing the other day. It starts off the same way, but this time instead of actually using an angle, you're just manipulating this. What could you do first? Well, I could multiply the secant through on the other side. So I'd have secant times 1 and secant times cos. So I'd have secant theta plus secant theta times cos theta. Is it the same as the other side? Not yet. What could you change? We could change secant to 1 over cos, right? Do you want me to change them both? Yeah? Okay. So we have 1 over cos plus 1 over cos times by cos. And you could make this cos over 1. So if you're multiplying fractions, you're going to be able to simplify. Can you see that these coses are going to simplify and go away? And now we have 1 over cos theta plus 1. We're pretty close. On the other side, we could change the secant to 1 over cos as well. And now they're identical. And by proving it, we show that it works for all values. So sometimes you're going to be asked to verify and plug in a value and get them to look the same. Sometimes you're going to be asked to prove it. So if we look at our second question. Move this right in the middle, split it up here, and we're still verifying it for when it's equal to 30 degrees. So we would have 1 minus tan of 30 degrees, cotangent of 30 degrees, minus 1 over cotangent of 30 degrees. So which is the easiest one to figure out? Tangent of 30 degrees. What is tangent of 30 degrees? Root 3 over 3. What does that mean cotangent is? 3 over root 3. Now that fraction work that we had before comes in. If we can write both sides as a single fraction, maybe we'll get close to showing this. On the left-hand side, how would I get a single fraction on the left-hand side? I'd need a common denominator. I could get a common denominator by changing the 1 to 3 over 3. And now that I have a common denominator, this side will become 3 minus root 3 all over 3. In the second side, on the right-hand side, do you see that I have a fraction over a fraction? Well, I have a fraction on the bottom, but I don't have a single fraction on the top yet. So if I first get a single fraction on the top, what would I need as a common denominator? I need a root 3, so I'd multiply this one by root 3 and root 3. Then my fraction on the top becomes 3 minus root 3 all over root 3, divided by the bottom I have 3 over root 3. Now that I have a fraction divided by a fraction, I can multiply by the reciprocal. Some of these questions take a lot of space just because you have lots of fractions. So I can have 3 minus root 3 all over root 3 multiplied by root 3 over 3. Can you see that this is grouped together? Do we have any factors that are identical? Yes, the root 3 and the root 3. So those can simplify. Is that the same as the other side? Yes, it is. So we just verified it for one angle. And it was a fair bit of work. Now we're going to see if we can prove this one. Is it okay if I erase? So now for proving it, well, one of the things that we're going to learn as a strategy for proving is very hard to prove things when you have different functions on different sides. Is there any way we could change this so we have the same function on both sides? Okay? You could change tangent to cotangent or cotangent to tangent. Which one are you probably more likely to do? So you're going to say I'm more likely to change cotangent to tangent, so I'm going to start with that. That would look like this. Can you see that we have the same kind of thing that we had before? We have a fraction on the bottom. So if we can get a single fraction on the top, by making this 1, I'd have to multiply by, to get a common denominator, tan over tan. Then on the top, I'm going to have 1 minus tan theta over tan theta. And on the bottom, I'm going to still have 1 over tan theta. When you're doing proofs, it's a good idea to leave a little bit of space in between your lines, Because if you don't, your fractions that have fractions and fractions and fractions, they might, the next line you might steal from the previous line without even knowing it, and your organization might go out, and then you're going to make some mistakes. So I leave a little bit of space in between. I also try to make my main dividing line longer than my other dividing lines. So I remember, oh yeah, that's the one in the middle. So I can see my fraction on the top and my fraction on the bottom. And now that I have a fraction divided by a fraction, I can multiply by the reciprocal. Now this 1 minus tan theta, that's grouped together. Do I have any factors that are identical? Yes. Tan thetas. So they can simplify. And then we're left with just 1 minus tan theta. Is that what I have on the other side? So I can say my left side is equal to my right side. And we're done. Now, what I like about this question is it teaches you that it's a good strategy to change things on one side of the equation to the same function as the other side of the equation. And we did that by changing the cotangents to tangent. I'm going to erase this now because we also said you could have changed the tangent to cotangent. What would have happened if we did that? Would the proof have been shorter? Would it have been easier? What would it look like? So if I changed tangent to 1 over cotangent, this is what I would get. On the right side, you see that I have a single fraction. On the left side, I don't have a single fraction. And one of the key strategies in this that we're going to do over and over again is try to write both sides as a single fraction. So how do I get the left side to be a single fraction? I need a common denominator. This will be cotangent over cotangent. Done. That's actually a nicer proof, isn't it? So then I could say left side equals right side. And this is probably the nicest proof, the shortest proof, instead of changing the other side to tangent. Another strategy that's going to come up that you're going to use a lot is everything can be changed to either sine or cosine. So this one, that could have been another strategy that you would think of. I'm going to change everything to sine and cosine. This is probably the messiest strategy in this example, but often is the best strategy to use. So if I changed tan to sine over cos, and I changed cotangent to cos over sine, and on both sides I said I want to get a common denominator, I want to get a single fraction. How am I going to get a single fraction here? I'm going to have to multiply by cos over cos. And on the left side, my single fraction looks like this. How am I going to get a single fraction on the right side? Well, I'd have to get a fraction over a fraction first, and then multiply by the reciprocal. If we make this one sine over sine, if we make that one sine over sine, then on the top, you would get that. On the bottom, you still have cos over sine. Now I have a fraction divided by a fraction, and I can multiply by the reciprocal. When I do this, this one gets grouped together because of the minus sign, but these are identical, so they'll cancel out, and we get cos theta minus sine theta over cos theta, which makes them equal. So that also works. So in this proof, the idea is there's many ways, many right ways to start. Some of them do take longer than others. So sometimes you look at a proof and try to make a decision, what do I think will be the shortest way to prove this? And try that. But there's going to be some times that you choose a method that might be a little bit longer, but it's not wrong. This is just as right as changing to cotangent. Yes? You can change the ones as well, because 1 is equal to sine squared plus cos squared. So that you can do as well. That sometimes makes it bigger, right? And anytime you make it bigger, sometimes it makes it more complicated, but sometimes that's the strategy you need to use. I want to show you something else. What we did here on the right-hand side, right, we got a fraction on the top, a fraction on the bottom, then multiplied by the reciprocal. That's a great strategy. It's awesome to use. You're going to use it a lot. Sometimes, though, when you get a common denominator by multiplying by sine over sine, what I did in green there was multiplying by 1. Does that make sense? And when you multiply something by 1, it doesn't change what the fraction's equal to because you're multiplying by 1. So one of the things that we're going to find out is multiplying by 1 in a variety of different ways is going to be an important strategy. So here I multiplied by sine over sine because I wanted a common denominator. I'm going to take that sine over sine. There we go. Make it a little bigger. Now I'm going to multiply the whole fraction by sine over sine. Can you see that I'm still multiplying by 1? But if I multiplied the top fraction by sine, what's going to happen? That sine's going to multiply that 1, and it's going to multiply by that. What am I going to get? Well, I'm just going to get cos theta with here, right? Because the sines are going to cancel. And when I multiply sine by that one, I get minus sine theta. What happens on the bottom of my fraction when I multiply by sine? It cancels out with that sign. Isn't that pretty? Done. And that made that even quicker. Now left side's equal to right side. So depending on how you multiply by 1, you can make your proofs longer, shorter, or easier. So now we've seen 4 different ways to prove this one. You just have to do one of those. Come up with any way. But the nice thing is if you have an idea, and as long as you're not making up anything new and unproven, you can use it. So you're allowed to use any of your identities to solve. Okay, the ones you can do from this question are 3, 5, 6, and 7. Ay, ay.